Now let's talk about supervised learning. So let's get first with an example. So let's suppose that we have a class that is corresponding to the concept of family car. So we are looking at different types of vehicles and we want to classify them. And let's say we have a family car. Let's say that in fact we have a two-class problem. The positives, what we will give as red circles here, are family cars, and the negative are other type of vehicles, not family cars. So, and we will represent this data with in 2 dimensions. So we have as x1 the car price, and as x2 the engine power, and we want to classify, want to do some processing according to this. So in our 2 classes problem, let's assume that we have things like this. We have a bunch of cars, and the red circles here are really the family cars that we have in our database, and all the others are not family cars. The way we will formalize this, we will model this for our example, and in general for the course. This is not the only way, but one way that is kind of coherent, especially with the Alpine book that we used before, and it is still available as reference for the course, is that we will model the data as x bold, which is a vector. So we have a vector x for representing the data, which according to x1 and x2 here, if we have more dimensions, we can go up to xd, which are the different values of the variable describing the data. And we will define as the class labels the R variables. Variable R here is either 1 or 0. So if x is positive, if it is a family car, it is R is equal to 1. Conversely, R is equal to 0 for negative cases, for x's that are not family cars. And that is put into a data set, which we call big X in calligraphic font. So this big X is in fact a set of n instances, so t from 1 to n. So every element is in fact a kind of pair of x trt. So here the t is not an exponent, it's really just an index. So this is the index of example tx. So the x example for the tf sample, and the R is the associated label to that TF sample. So from that, we will define some classification hypothesis. So let's say that we are using a box model. This is not a common model, but for the sake of example, let's use that. It's kind of convenient in terms of representing our model. So we see that we are defining our hypothesis, our model, as a box, and this is parameterized according to the low left corner, so which is like the x1 min, x2 min parameters, and we have also the top right corner, which is x1 max, x2 max. So with these 4 real values, we are able to define the shape, the type of model hypothesis we are using for our example. So we can say we have some particular hypothesis here, small h, within the space of possible hypotheses, the big H in calligraphic font. We see that hx is equal to 1 if class x is positive. Likewise, it is 0 if class x is negative. We also have what we call the empirical error. So we have the error of our model H. So let's say that we have a given H here, which is test on the data set X here. So this testing can be done empirically by saying, okay, let's make the sum over all the samples of X. So from t to 1 up to n. So we are testing everything that is here. And we are putting this in a loss function. That loss, which is like the big L here, is a function that is evaluating the kind of error between the prediction. So the prediction is the HXT here versus the real label, which is the RT. So there are many ways to compute the loss. I would say the standard basic loss is not the only one, but the classical one is the 0-1 loss, which is basically giving a 1 if A is different from B. So like I said, for example, if HXT, the prediction is different from the real label, we have a 1, which is a kind of an error of 1, or 0 if it is the same, if the prediction is the right label, is the ground truth label. So with this function here, we are evaluating the average error over all the data set. So we are summing for all instances, multiplying by 1 over n, so dividing by n to get something between 0 and 1. So this is an example of empirical error. So we can see that we have a general and specific hypothesis. So let's say that G is the most general hypothesis here, and S is the most specific. So let's say that if we want to get model data for which there are no errors, we have the two extreme cases. So we have the really narrow box here, which is defined by S, which is the box in where everything is white inside except the samples. This is the most specific, you know, the one that is really touching the positive data in terms of placement. This is the smallest we can get. And the opposite is the G box, which is the one in dark gray here, which is the largest possible. You know, it is kind of touching samples here. So it's really, really close to these samples. So it is the biggest we can get, the most general. It tends to put everything as positive with a model that is the biggest possible. Bigger than that, there will be some classification errors. And all the hypotheses between S and G are part of what we call the version space. You know, we have an infinity of models in between that all have the perfect accuracy. They have 0 errors, but they are different. They don't necessarily have the same parameterization. So the point here is that we don't, I would say, there's not necessarily a single solution there. There might be many solutions with the same performance. And so the point is to say, okay, what is the right one? What are the right solution to use? Also, we can see that sometimes generally we have noise within the data. So though the data can be not perfectly accurate according to what we have, we can do some labeling errors. You know, some human labeler may mistake some data as not the right thing. In fact, the label provided is not the real label. There are some kind of errors in the measurements. This is more like an accuracy. You know, some instruments are not measuring super well or are sensitive to some situation. There can be some latent measurements. In fact, maybe X1 and X2 here might not be enough to describe well the model. We may need more variables to capture all different aspects. So this can be said as a kind of noise, even though it's not really a noise. It's more that we don't have these measurements, and while these measurements are determinant in terms of doing the classification test, for example. But one thing we are looking at is that when we obtain equivalent performances, when the performances are equal, we tend to always prefer the simplest model, because that simplest model is more likely to provide a good explanation, a good modeling of the task. So with simpler models, the training is usually much easier. It takes less time. The models are more efficient in terms of processing and in terms of use also. Smaller models may be easier to interpret, even though full interpretability may be very difficult. We can get some sense of what's going on and be able to validate that this is right in terms of simple models. Much complex models, it's not the same thing. We often just don't know. It's a black box, and we need to deal with that. I would say the one strong argument is coming from Occam's razor. For those who don't know that, Occam's was an English philosopher, which stated these things that everything else being equivalent, we should choose the simplest solution, simplest explanation, because this one is the most likely. We presented the two-class situation. We can extend that to the multi-class situation where we don't have only two classes, we have k classes. So in that case, let's say that, for example, that we have three classes here on the left, which are like the diamond greens, the blue squares, and the red circles. So these are two different classes. In general, we will say that we have a modeling of a data set big X here with n instances that is described by its input, its X data, and the associated labels. Given that we have more than two classes, we will in fact represent the labels as a vector of k dimensions for k classes. Each element of a vector is 0 or 1. So it is really a binary vector, and we constrain it to have one value equal to 1 and all the others equal to 0. This is what we call often the one-hot vector. So we see that RIT, so it's basically the label for class I of instance T, is equal to 1 if xt is part of class Ci, and 0 otherwise when xt is not part of class Cy, for example. And then in such case, a basic solution for training is to train k hypothesis. So let's say that we have k classes. Let's train one model per class. This is not the only solution, but this is, I would say, a simple solution to use. And the point is to see that our HI, I is the class associated to that hypothesis, is telling us whether or not that instance is coming from class I or not. So if it is, HI is equal to 1. If it is not, it is equal to 0. Again, it is coming from a different class. Also in supervised learning, we have regression problems. So let's say that we have a data set with XT-RT from data from 1 to n. The difference here is that the RT are scalars. So in real values, so RT is part of our real values domain. So we are looking for a function h that is able to learn to make the prediction equivalent to the RT, but we can assume that there is some kind of epsilon level of noise or level of error. And there we want to learn usually using different, there are possibly different criterion. The one that is, I would say the classic one is the quadratic error. Basically, it states that the error of a model H on a regression data set big X here is equal to getting the square difference. You know, we have the target. This is what we want as output. This is what we obtain as output. The HXT is the prediction. We compute the difference and we put it at the power of 2. And then we are making this sum over all instances, averaging, dividing by n for averaging this result. So this is the quadratic error. We can do regression in many ways. We can do what we call polynomial regression. Basically, the H model is represented as a polynomial of order something. So with first order polynomial in 2D, we have something like this. In fact, it is in 1D in terms of the input. So we have 1D input, 1D output. So it is in 1D. In fact, we have the function h over scalar x, which is defined as w1x plus w0. So this is a super basic linear equation that you know quite well. And then our point is to say, can we estimate the right values of w1, w0 based on the empirical error? So this is the way we can proceed. We can see here on the figure that we have the ground truth here. So we have a quadratic model with the points. This is the basic element. And the points are the real data that we collected. If we are using some first order polynomial, so this is like the dash red here. So we get this line, these straight lines. This is what corresponds to our equation here, the kind of model we can obtain. The W1, W0 may vary from one example to another. What we can see here is that clearly there is some underfitting. You know, the points are not linear. They are more, I would say, following some kind of quadratic model. So we can see here that we have underfitting. If we go on the other side, on the lower right, we get fourth order polynomial. So in fourth order polynomial, we can get, I would say, a perfect, an almost perfect solution. We see that the learn curve is passing through most points, except here we have some cases where there are some small error, but basically the curve is really close to all the points. So we see that it is almost perfect, but probably it will not generalize well. We just have to look at the extreme cases in terms of extrapolation here. Can be quite off if we assume that the linear model, especially here, if we kind of extrapolate that way, while the reality is going there, it will be really bad in that on the left regions. So possibly it is not a good model in terms of generalization. There are what we call some overfitting. And to finish, we can say that in fact, second order captures data better than the first one, while not being too strongly fit on the data. So there are not likely to be overfit here. It seems to be a good model complexity. What we can see in supervised learning is that we are facing an ill-defined model. So it is not a well-defined. The example here are not enough for a unique solution. So we can get many solutions with the same samples. We must have an inductive bias in that case for making some assumptions on H. So with that inductive bias, we'll tend to get some type of models that are particularly good in terms of generalization, for example. So the first objective is generalization. We want to get a model that is performing well on new data. So in terms of overfit, H is more complex than the model, the concept. So it means that when we are overfitting, we have models that are too complex to what we have as instances. So this is not good because overfitting tends to memorize or catch some relations that are not real relations between the data. Conversely, when the H is not complex enough, we have cases of underfitting. So this is the example of linear model. So H is less complex than the concept we try to model. So we need not to forget that the point here is to minimize the generalization error on new and unseen examples. So we want to learn models that are minimizing the generalization error, not necessarily be the best one on the training set we have at end. So we need to figure out what is the complexity of the hypothesis class. So what we see is that at first, when we are doing underfitting, as we are increasing the complexity of the model, we tend to be better and better in terms of generalization. But as we get over the good complexity, when we get into much more complex models, where there are some overfitting, the generalization error starts to decrease. So we have some degradation of performance on with too complex models, while we have also generalization errors in terms of only performance in terms of too simple models. We need to find the right trade-off. The second factor that is super influent also is the size of the training set. So the more data we have, the more the generalization error will decrease, because we have much more samples that are covering well the input space. So we can fit better in many regions compared to having really small data sets where we just have a few samples here and there. So many situations in between will not be covered by the training set. And then what we learn as model may not be the best. So we are in an era of big data, and the fact of having many instances is really a good thing. Another aspect that we are looking at, and it's often a way to deal with this kind of trade-off between being too complex or too simple, is to make use of what we call regularization. So this is the idea of introducing in the optimization criterion use. So we have an optimized function. We try to optimize to fit the parameters of the function on the data to get the best results in terms of generalization. We can include a factor of complexity. So we want to get the best performance in terms of empirical error on the training set, but at the same time, we also want to minimize the complexity. So that's in line with Occam's razor. So all other things being equal, the simplest solution are the most likely. So with two almost equivalent solutions, if one is much simpler, we can optimize with regularization, and we will follow on that one because the overall function will include performance and complexity. So we want to minimize error, but also we want to minimize complexity in our optimization. So a common form is to say, let's use a J function, which is made of E here, which is the error function or the loss function, plus some lambda, which is kind of arbitrary relative weighting between the empirical error and the complexity of the function. So we want to weight error versus complexity through this lambda factor. And that is important to adjust the lambda in such a way that we will get more complex models if there are some decrease in error, but at equal performance, we tend to minimize complexity. So there are many complexity measurements used for regularization. One simple thing is to say, okay, let's just count the number of used parameters, and all the zero values are not counted, and we want to minimize the number of non-zero values. That's a simple thing that has been used. Or maybe the L2 magnitude, this is a little fancy. It's more compared to the first one is to say, let's use the value squared. That means something because higher values is, let's say that a value A is two times bigger than a value B. In terms of being squared, it will have 4 times more impact. So we tend to say we not just want to get values at 0, but we want to get values relatively low. In several models, that means that the model will be less complex. There is also the Vapnik-Chevron and Kiss dimensions. This is a rather elaborated theoretical approaches. The point is that this is measuring really the capacity of the model to classify well complex settings of data sets. So we say we are able to really separate well two classes according to any kind of combinations, and we have some level of this that is what we call the VCDIM, the Vapnik-Chevron and Kiss dimension. That is really a measurement that is also used in terms of developing theoretical bounds on the performance of models. Or, for example, with the polynomial regression example we saw before, the degree of the polynomial use is something that is meaningful for that. We also have some, the point of using empirical validation. So sometimes to evaluate the generalization error, we need to use data that are unseen during validation. So a classical approach for that is to say, let's split the data set in 3. So let's maybe, these are arbitrary values, can be quite different, but let's say use half of the data as training, 25% as validation, 25% as testing. So it's a 50, 25, 25. And the point is we are training on the training set. So we use the full training set to learn a model. And then we are evaluating the different models we obtain on the validation set. Here to be sure that we are picking models that are not just good in terms of training, because they can overfit a lot and be super good on training, but being bad at generalizing. On the validation set, we expect to measure generalization. The point is, if we test many models on validation set, we somehow capture elements of the validation set. But that's not perfect. So in the end, once we have one great model, we can say, okay, test is a great model, and we can expect to get that performance based on the test set. So the test set is really used at the end to evaluate the generalization performance expected for the final model found. And this can be used to compare our approach with other approaches that are reporting results on the same test set. If we have only few data, the point of that, like I said before, bigger the data set, better the model, better the learning. Here we are cutting at least in half the training set. So we can use 2/3 for training set if we wish, but anyway, in all cases, it means less data for training. When we have already really small data sets, removing more instances can be really hurtful in terms of performance. So we can use different strategies. One of these is to say, okay, let's split the complete data set, the 100% data set, in m distinct folds. So each fold is about same size, sampling, well uniformly distributed over the classes, over everything. So it tends to be really similar from one fold to another. And then we will make a training where we will use m-1 folds as training and the remaining fold as validation set. And we will repeat this m times. So every fold will be used once as validation set. And at all time when we use one as validation set, all the other folds are used as training set. And we are repeating this m times, and we take the best case on average over this m times as configuration, and simply this is good. This is the evaluation of the performance of our model, and we can retrain this best model on the complete training data set after that. Some extreme cases is to say we use as much folds as there are data. So every single instances is one fold, and we are repeating this n times. This is what we call leave one out. There are in fact 3 dimensions of supervised learning. We can see this like we have an element that is the representation. So we have parametric hypothesis, the h of x given the theta. So this can be different things. This is basically the data structure of the model that we are looking for. So we can have instances-based classification, hyperplanes, which are kind of cutting the space into decision trees, set of rules, neural networks, graphical models, whatever. So this is really one of the 3 basic elements of supervised learning. We also have the evaluation, so the criterion we are using to optimize the model. So this can be the empirical error, but there are many other measurements we can use to guide the learning, the recognition rate, the precision. So this is basically the opposite of the error. It's 1 minus the error. Precision recall in terms of detection, quadratic error in terms of regression, likelihood with probabilistic models, posterior probability, information gain, margin, cost, whatever. So these are different criteria that will optimize slightly differently. And these are, in fact, they should be, I would say, usable with the optimization procedure. So basically, often the 3 things are often designed to be working well together. So we tend to use an evaluation function that is fit for the optimization, that is also good to optimize over the model, the representation we are using. The optimization is basically to say we are looking to find the optimal theta, the theta star that is minimizing the empirical error, for example, over all possible parameterization. So we have here our criterion for use for optimizing. So we want to find the theta here that is minimizing the error on the training set. This is a theta star, and we can use things like gradient descent, quadratic programming heuristics for figuring out what is the theta star to use here.